Welcome to This Explainer. Look, if you're tuning in, you already know that large language models have completely revolutionized how we interact with text and code. We use them every day. But behind the scenes, top AI researchers, including Turing Award winner Yann LeCun, are making a pretty bold claim. They're arguing that simply predicting the next word is actually a dead end for achieving true artificial intelligence. So today, we are unpacking a massive paradigm shift. We're talking about the move away from token prediction and diving headfirst into world models and something called the Joint Embedding Predictive Architecture, or JEPA. To really wrap our heads around why this shift is happening, we have to ask a question that's probably crossed your mind. We've all seen it, right? Today's AI can write flawless, incredibly complex Python code, it can easily pass the bar exam, and it can write a sonnet in seconds. But it doesn't intuitively grasp that if you push a glass off the edge of a table, it's going to smash on the floor. It has all this massive computational power, but it completely lacks what you and I would call basic common sense. When you stack up current machine learning against biological intelligence, the contrast is honestly a little shocking. Think about a robotic arm versus a crow. Current ML systems, especially supervised and reinforcement learning models, are incredibly specialized, but they're so brittle. They require an insane number of trials just to learn one specific thing. Humans and animals, on the other hand, we learn new tasks almost instantly because we inherently understand how the physical world operates. Biological brains can do complex chains of reasoning and actually plan out subtasks on the fly. Current AI? It simply doesn't do this. So the crucial takeaway here is that this lack of common sense stems directly from the very architecture of current autoregressive LLMs. They generate data one single token or word at a time using a fixed, constant number of compute steps. And because they're just guessing the next token, there's a huge inherent mathematical flaw built right in. If there is even a tiny probability of error, let's call it E, with every single token, the chance that a really long sequence is perfectly factual diverges exponentially. The probability of being entirely correct literally drops off a cliff the longer the model talks. We get so easily fooled by their incredible verbal fluency, but beneath the perfect grammar, they literally have no mental model of the underlying reality. So, what is the fix? Well, enter the world model. Cognitive scientists have actually studied this concept for decades, and it's exactly what top AI researchers are trying to build right now to solve this whole hallucination and reasoning bottleneck. At its core, a world model is basically an internal simulator of reality. Think of it as a mental sandbox. It tells an AI agent what's likely to happen, what's plausible, and what totally defies the laws of physics. By using a world model, an AI can predict the consequences of its actions and plan out complex steps without having to physically do them first and risk making some catastrophic mistake. Now, Yann LeCun's proposed architecture for autonomous intelligence is fascinating because of how biological it feels. Notice that the world model sits right at the center of everything. It takes inputs from perception, basically what the AI is seeing in the moment, and uses that data to predict future states. It then feeds those predictions over to the actor module, which helps it plan actions that minimize cost or, discomfort. So instead of just blindly reacting to prompts, the system is actively simulating the future before it makes a single move. But actually designing this internal simulator, that is notoriously difficult. Our universe is incredibly messy and chaotic. If you drop a pen, you know for sure it's going to fall, but you can't predict exactly how it will bounce when it hits the ground. Because of this, a world model can't just memorize one strict deterministic path. It absolutely must be able to hold multiple plausible futures in its mind at the exact same time. It also has to predict things at different timescales and levels of abstraction, like ignoring the exact pixel color of the falling pen and just focusing purely on the physics of the fall itself. To actually build this kind of predictive engine, researchers needed something entirely new. Say hello to JEPA. We simply cannot waste massive amounts of compute power predicting individual pixels or text tokens. Instead, JEPA, which stands for Joint Embedding Predictive Architecture, takes a radically different approach. It is a non-generative, self-supervised learning architecture. And guys, this is a massive departure from the generative models we're used to, like GPT-4 or Midjourney. JEPA flips the script. It teaches AI to predict the fundamental, abstract meaning of a scene, rather than obsessing over perfectly recreating every single raw pixel or exact word. It is all about grasping the concept, not regurgitating the data. Looking at the blueprint for JEPA, the flow is really elegant. It takes a context, let's call it X, and a target, Y. Imagine these are two sequential frames of a video. Instead of trying to predict the actual next image Y, it passes both frames through encoders to create abstract embeddings. Then, a predictor module tries to guess the embedding of Y based solely on X. But the real magic is this latent variable Z. It represents the unpredictable elements of the real world. It basically injects just enough uncertainty into the system so the model could imagine multiple valid futures without completely breaking down. A great way to think about this is imagining a partially covered painting. If you ask a generative AI to tell you what's hidden, it will painstakingly try to recreate the exact brushstrokes pixel by pixel. That is incredibly hard and computationally so wasteful because the exact placement of those pixels doesn't actually matter for understanding the picture. JEPA, on the other hand, it just looks at the visible half and efficiently summarizes what the hidden half probably depicts. It guesses the meaning, not the pixels. When we put these two head-to-head, the fundamental shift becomes so clear. Generative AI is hyper-focused on recreating raw data, while JEPA is laser-focused on predicting abstract meaning. Because generative AI is stuck operating in pixel or token space, it wastefully processes a ton of irrelevant noise. JEPA operates purely in latent representation space. And the result? JEPA ruthlessly discards all those unpredictable details to focus entirely on the core structure of the world. It basically trades the ability to generate pretty pictures for a massive, massive boost in semantic understanding. Generative models require a really bulky decoder just to reconstruct the original data, and they measure their success by how perfectly the pixels match. But JEPA skips the decoder entirely. It measures success by how well its prediction matches the abstract encoding of the truth. No decoder, no pixels, just pure abstracted meaning. Okay, so that's the theory, but where do we actually stand today? Let's take an objective look at the pros, the cons, and the major players building this out. The timeline here has been nothing short of breakneck. JEPA went from a purely theoretical paper by Yann LeCun in 2022 right into a functional image model by Meta in 2023. By 2024, they dropped VJEPA for video, literally allowing AI to understand physics just by watching video clips. In 2025, VJEPA 2 scaled this up into a true world model capable of zero-shot robot control. And now, in 2026, we're seeing massive commercialization with billion-dollar startups like Ami Labs strictly dedicated to building out this autonomous vision. The pace is just wild. And look, it's not just a niche meta research project anymore. This idea spread like wildfire. The entire research community is adapting the JEPA design pattern because predicting abstract representations applies to almost any signal out there. We've now got AJEPA for audio, MC-JEPA for motion and optical flow, and researchers are rapidly deploying this architecture to process 3D data, complex time series, and even geospatial analytics. It's proving to be incredibly versatile. But we have to be real about the hurdles. It's not a perfect system yet. JEPA has a glaring weakness right now. It is largely absent from natural language processing. No JEPA model beats autoregressive models like GPT-4 when it comes to pure language tasks. Plus, engineers are constantly battling something called the collapse problem. This is a super tricky bug where the AI realizes it can basically cheat on the test by outputting a constant blank vector for every prediction, getting a perfect score without actually learning a single thing. Also, while robotic planning with this works, it's mostly in highly constrained laboratory settings so far. It's cutting-edge research, not a boxed consumer product. Which brings us to the ultimate question. What does this mean for the future of AI? Are we just tossing our LLMs in the trash? Absolutely not. The consensus isn't that JEPA will kill the LLM. Rather, we're looking at a highly complementary future. LLMs have undeniably mastered language, logic, and code by essentially reading the entire internet. But JEPA is designed to be the missing puzzle piece. By watching video and observing the physical world, it learns the intuitive physical laws that text-only models desperately lack. Together, these two paradigms are paving the way for true autonomous machine intelligence. And that leaves us with the ultimate question that will define the next decade of AI development. Will learning to predict the world in the abstract, rather than just guessing the next word, finally bridge the gap between impressive machine calculation and genuine human-like common sense? It is literally the billion-dollar question, and the race to answer it has already begun. Thanks for joining me on this explainer, and definitely keep an eye on how these world models evolve.